All right, again, welcome everyone. I'm Susan Grant Harris. I'm Senior Communications Advisor with New Buildings Institute. We're glad that you could join us for this special event, our Sustainable Commercial Refrigeration webinar. This event is being recorded. A link will be provided to the recording and presentation slides later this week. We're going to have time for questions after our panelists' presentations. Please note on your dashboard that there's a button for Q&A. Put your questions for our panelists there so that we can find them and be able to ask them at the end. For general chat, please use the chat functionality. Feel free to chat with each other and put any comments or questions that you have for each other in the chat. This event is made possible by the San Diego Learn program. Learn offers free energy efficiency and electrification courses. These short courses are designed to support you in upskilling and gaining new knowledge. Visit them at sandiegolearn.com. Here we have a snapshot of the things that we'll be talking about in today's webinar. Commercial refrigeration is essential to many industries, from food to healthcare. However, as many of us know, refrigerants and the high energy demand can be problematic for the environmental impact and the cost. There have been technical advancements and code changes to move us forward in another way. Today, we're going to focus on sustainable commercial refrigeration and a project case study of a fully functional CO2 heat pump. Our panelists will discuss the innovations that improve energy efficiency, quality, and overall performance. These are our panelists with us today. We've had a slight change due to a family emergency that Carolyn was not able to join us, but we do have Doug Davenport, the founder and CEO of Prospect Silicon Valley. Also with us today is Sean Jarvie, Chief Technology Officer, Flow Environmental Systems. With 20 years of experience working for original equipment manufacturers of all sizes, Sean has developed a unique perspective and a deep understanding of the HVAC and refrigeration industries. And also, Rongjin Yin, Technology Researcher 3, Grid Integration Group, Lawrence Berkeley National Labs. Working within the energy technologies area since 2010, he has contributed to the development of tools for rapid demand response assessment in commercial buildings, cold storage, and refrigeration warehouses. And with that, I'd like to pass the microphone to Doug. Doug, please get us started.
Okay, thank you, and good morning or good afternoon to you, depending on where you're coming in from. I'm here in the Bay Area and excited to talk to you about our work that we're doing in this realm with some really great partners. So refrigeration and cold storage, and why does it matter? Well, first of all, when you think about the entire food processing industry, refrigeration is a massive portion of the overall energy and electricity usage for that sector. So it's a third of the electricity use. Demand for cold storage is certainly expected to increase, not just in the food production sector, but in grocery, in pharmaceuticals, schools, and others where food is being served, and especially even in emergency infrastructure where food and drugs need to be stored. Refrigeration is just going to be a continued and increasing part of life. And so, looking for ways to reduce the environmental impact of this is very important. So, our colleagues at the California Energy Commission certainly recognize the need, and in partnership with the California Air Resources Board issued a funding opportunity to look at new solutions. And we'll be talking about those. So, here what we're trying to address is, high power demand, refrigeration load, which I'm sure that my colleague Sean will be talking much more about in terms of refrigerants, the number of alternatives to the current use of refrigeration equipment is actually somewhat limited. So a new solution is needed. These are high throughput, always on kinds of solutions in a world where demand response is very, very important. So, the current set of equipment is not as sensitive to being able to respond to high demand or respond to high power price signals. And so that's another really important part of what we're doing. We can go to the next slide. So, advancing innovation here, our partners at Flow Environmental Systems, which was an engagement that we took on quite some time before this opportunity arose, really impressed us with the completely outside the box thinking about design and both the integrity and the brilliance of the design of the system. And we felt that this was something that would not just be bringing a technology solution to the fore, but really bringing a new kind of line of thinking around these solutions to the fore. So we were very excited. So the California Energy Commission funding opportunity that I spoke about was energy efficiency and load flexibility in industrial and commercial cold storage facilities. What we really needed here was to have a very rigorous and scientific system demonstration, not just it works, but here are the 30 ways that we can show you how it's performing with third-party verified data. That brings in our partner, Berkeley Lab, and Ranchan Yin, who will be speaking later. Having really strong advisors and design engineering reviews across the board as we do this project, not just in terms of the design for the installation and running of the demonstration, but really just the overall kind of, let's say, design thinking around how this would be applied in multiple other situations was highly important. So we've assembled an advisory committee of, I want to say it's in excess of 25 engineering firms, operating firms, nonprofits that are dedicated to decarbonizing this sector, and a lot of other very, very strong experts. As we do this project, we're actually forging design guidance and reference information that'll be immediately transferable to other applications, which is incredibly important to us. We include contractor and engineering training through our partner DMG North, which was brought to us by Flow. DMG North has an ongoing Northern California training center for contractors and engineers in the heat pump space that will be targeting applications here for refrigeration. We will have comprehensive industry outreach. You're witnessing it right now, folks. This is really, really important to us, and we want to have as broad and as deep a participation as possible in this, in this overall effort. And we want to speak with you about the projects that you're working on and be a helpful bridge to the knowledge and information that we bring. So let's go to the next slide real quick. So here's the team. I'm proud to say, and one of the things that Prospect Silicon Valley does very well is find really important, compelling problems and find really, really high quality and compelling expertise to bring together into a team. No one firm could have pulled off what we've pulled off together, and what we're going to do is very important from that standpoint. So Prospect Silicon Valley as the catalyst and the organizer and the project manager and the ringleader and the conductor of a campaign around this effort is very important, but it would be nothing without Flow Environmental Systems and their technology, and DMG North and what they do in terms of connection to the industry and training. Berkeley Lab is just unrivaled technical expert in this space, and a deep partner to us in measurement and verification and research and lots of other areas. Strauss Family Creamery, if you're in the Bay Area, is a very well-known established name. Not only are they known for just very, very high quality food products, but they are a leader in sustainability. They and the owner, Mr. Strauss himself, came to our meetings because he's personally committed to showing how this industry can move forward by lowering its greenhouse gas footprint and also being able to maintain just an extremely high standard of quality. So we're very, very proud to be working with Strauss. Our engineering partners at Alter Engineers and Ideas Consulting are very, very strong experts in mechanical and electrical engineering, and they'll be putting together the design packages for installation of this system. Avita Energy and Mr. Aaron Daly is a veteran of energy management in the grocery sector and food production sector, and is a very strong advisor and consultant to us in this effort. Just real quick, because I sense the time is moving forward, this is actually part of a pair of demonstrations. So to the right, you see a commercial cold storage application, and that is Strauss. A vast number of products are coming out of a single facility, which is kind of amazing. But within that, there are multiple cold rooms and freezing rooms. They obviously have supplemental process hot water, and we're bringing hot water to the system as part of our refrigeration project, which I know Sean will talk about. It's pretty amazing. We're bringing in advanced defrost, which is really important to the energy efficiency, and we're bringing in grid responsiveness, which is not possible today with the current system. So we're doing some fairly innovative things there. That's paired with an HVAC application of the very same heat pump, smaller scale, looking at simultaneous heating, cooling, and hot water from the heat pump in a large office HVAC simulation using Berkeley Labs Flex Lab facility, which is a pretty cool place. Let's flip the pictures and I can show a couple of things here. So we take this very seriously, and Berkeley Labs Flex Lab facility is so realistic and so heavily instrumented. They even include dummies in their office setting, test cells, heated to 98.6 degrees. So this is as close as you can come to a working office, and is heavily, heavily instrumented so we can get really deep data on the performance of the system. I think you can flip one more picture there. In the Strauss demonstration, as Sean will talk about, we're applying the heat pump. We're including defrost water and optional hot water to the facility, as well as possibly building heat systems and CO2 storage in order to serve a freezer hardening room at -30 to -35 F and 2 cooling rooms at 35 F simultaneously. This is going to be, I think, a very important project. And I will just mention that our friends at Sonoma Clean Power, the local utility, are using this project as an important data point for their industrial grid demand response program. So this demonstration has many leverage points across the industry and the region. Is this still me, Susan? Okay, this is what happens when you come in at the last minute. So, I think I'll just go through this really quickly. We're here to demonstrate a commercial cold storage solution that's going to vastly reduce GHG emissions, save costs, and improve energy efficiency and demand flexibility, which are features that are impossible with current systems today. I've already talked about the site and the kind of conditions there. The technology will be Flow's 60-ton heat pump system that will be used in demonstration mode and will be working actually in parallel with the current system. So there's redundancy. We are not going to upset the flow of dairy products from a leading brand in the Bay Area. And there is a thing called peak ice cream, which we will not violate because ice cream is never going to be in short supply in the Bay Area, thanks to us. There will be independent third-party M&V of this entire project provided by LB&L. We're going to create an abstract of that M&V in terms of its impact for open publication. And then we have a massive amount of industry engagement that will be going on across the board with great partners like NBI, the NASRC, and many other groups, as well as a network of engineering firms to make sure that we've got just the maximum amount of not just exposure, but contact and support from this project out to the next level of applications. One last thing I wanted to cover, and this will be, I think this is my last slide. One last thing that I'd like to cover, if you shift you can change slides. In these two projects and many others that we're working on, it's really important that our work is accessible, that people can have conversations with us, and they can join us in learning about the project and even getting involved. So we have a program we call Pathways. That QR code will lead you to our site. The idea here behind any of these projects is that there is an outreach campaign that is already going, even in our planning phases. We're trying to hit, as you know, a very complex industry when it comes to getting these projects done. So facility owners and operators, the engineers, the contractors, and both the public and private sector, including policymakers, are important to this conversation. So we're creating conversations and creating threads that are meeting the needs of each one of those. The results of this test and even a financial assessment of this test will be published and will be available to anybody who's involved. Design resources, including performance curves, a BIM model, a Modelica model, other kinds of information will be made available for designers. And there's a controls aspect to this that, is dealing with some of the demand response and other aspects. That beta will be made available, so that framework will be transferable to conventional on-market control systems. Every ounce of this project is meant to be packaged and made useful to the people who are needed to. So I'm very proud that Pathways will be a channel for that, and we encourage you, please sign up, register. You'll hear about meetings, you'll hear about things, not just these projects, but others, and we would love to have you involved. With that, I'm going to turn it over to Sean. Thank you so much.
Thank you so much, Doug. Right on schedule.
Thank you.
And I'm very glad to hear there will not be any disruption to the ice cream supply.
Absolutely not.
That is. And Sean, please carry on the conversation about this great project.
All right. Well, that was wonderful. Thank you, Doug. Thank you, Susan. Thank you for everybody being here. I'm Sean Jarby. I'm the Chief Technology Officer here over at Flow. And just a real quick high-level background, may or may not have heard of us, but we are a U.S. company doing environmentally responsible HVAC technologies and making sure they're all market viable. We are focused on decarbonizing, detoxifying, stopping burning stuff, and really serving the harder to electrify end use cases. That's exactly what Doug talked about here. That's high temperature heat delivery, simultaneous, outbreaking the grid, and honestly meeting some of the codes and regulations that are out there, because they are advancing a lot. Next, please. So I always like to ground it. I'm an engineer who likes to get things down to the beginning, and then we start building up and finding solutions. So the problem statement that we all face is buildings are 40% of all greenhouse gas emissions. And we're building a lot more, whether the industrial, commercial, and the commercial refrigeration sector might be more of this at times. So there's people doing the right things. We're partnered with wonderful individuals that Doug mentioned. The team we have is a dream team for me. I have so much fun every day working on this, but there aren't everybody doing this. So there are the regulatory hurdles that are coming. So as we kind of work through all these things, right sizing equipment, efficiency, and just stopping the burning of stuff, we're really talking heat pumps in the refrigeration space. We call them racks a lot of times. We're talking about refrigerants to make a dent in this huge beast we call greenhouse gas emissions. Next. So this is a slide with a lot of information on it, but it is helpful to see the lay of the land of where we are going as an industry. We've been through 5 refrigerant transitions to date, and last count I've seen, and of that, we are in the midst of another one. So right now, we have a number of key rubrics that our legislators and our rule makers have set before us. First one is greenhouse gas emissions, or GWP. Ozone, and that's basically global warming. Don't heat up the earth, please. Then you got ODP, ozone depletion potential. That's been out there since the Montreal Protocol. Don't put any more holes in the ozone layer, please. Safety class, which is your A1s or your safe, non-toxic, non-flammable solutions, aka don't blow yourself up and don't poison yourself. So that's really a nice thing to do. And then PFAS, or those forever chemicals that go into our water supply and cause all kinds of adverse health effects. And if you look across all these models, whether in HVAC or refrigeration, you see a very clear champion here with R744 and CO2. There are other good ones out there, and they're all specialized, but they require unique engineering solutions. So if we wanted to jump to the end and not do an intermediate step and another transition in the future, we have to be looking at naturals, and a lot of times CO2 is phenomenal in both categories. So much so that organizations like the International Institute of All Natural or Ammonia Refrigeration have changed their name to International Institute of All Natural Refrigeration because so many people are using CO2 in place of ammonia now. But there is a trick. So we are having to do a transcritical system versus a subcritical system. It is a little bit different, and that's why it hasn't had market adoption to date in a lot of the things I've seen. Next, please. So what does that mean for the nerdy people on the call who actually want to know the definitions? This is a pressure enthalpy chart. I quickly and promptly forgot it the moment I took the test and left having my college course. I relearned it later in life. But all you really need to know is this little red dot you see there called the critical point. All systems that are subcritical, all those other refrigerants you saw, they have to be less than that critical point for the max discharge pressures. That leads to a lot of design fundamental choices we have to make. While we can make good cooling, we can't always make good high temperature heating, and we have a lot of reliability issues with slugging and phase changes and stuff in the system. So if we're going to do something better, a transcritical system has a lot of really unique, innovative technology aspects to it. One is you can make high discharge temperatures and do that supplemental heating. You can do heating and take 100% sensible heat extraction from the environment and use a larger portion of that heat, up to 140% more than traditional systems. And then you can decouple temperature and pressure and now do some really wonderful optimizations, whether we're optimizing for cold, for hot, or somewhere in between and both in the same time. We can really dial that in. So next, please. And that's where we built our Answer CO2 heat pump. Next. So this is an air to water and a water to water system inherently. You can do refrigeration as well because we are using the exact same components that the supermarket and industrial industry has been using for 30 years. We've specifically designed it for HVAC duty first, and then we extended that operational range so that it can encompass a lot of these complicated refrigeration projects that play on this edge of refrigeration, HVAC, and heating systems. Now we can do domestic hot water without a problem. Simultaneous heating and cooling is really new, novel, and unique because we built a non-reversing system, and we can do hot water boiler applications with it. You set up a split and have long splits between it, or you can do it as a package system. Next. So we have a couple different configurations. Doug mentioned the smaller form factor earlier. That's our 20-ton model. That's going into LV&L to do a lot of the HVAC duty stuff. The exact same parts and pieces are now also being used in that middle figure you see there for Strauss and what they're doing on that project. That is the same box, same technology. It's versatile enough to work at -40 all the way up to 180 degrees or anywhere in between with the same exact product. So we can start bridging these gaps between industries. And then we have a lot of variability in the gas cooler size that we can do small tight form factor V-banks, small horizontals, go all from bottom, discharge up, and verticals where we can do pressurized plenums and things like that. Next, please. So without going real deep, we've built a system that now can be an energy engine in the middle of all this, or we can do low temperature heating, high temperature heating, cooling systems, whether it's high temperature sensible only, or low temperature comfort cooling, low dew point, or even freezing applications, all with the same product. We can engage energy recovery, energy storage, and geothermal energy, and seamlessly transition to an airside source or sink. And this system now is also ultra responsive because it's a little mini central plant in a box that we can make grid integration possible. So Ron's going to talk about that here in a moment, but there's a lot of potential there. So add it all up, we have a simplified system with very good natural future-proof refrigerants going to the future. We can make hot, we can make cold, we can make really high efficiencies and called COPs, no defrost. That's a whole nother topic, but it's really cool. No D rates for cold climates because of the nature of CO2. It's that much more versatile, seamless transitions, robust supply chains, and honestly, one of the lowest carbon emission projects you can possibly do. Next. So this is our HVAC unit. So I'm going to just share this briefly and then I'll turn it over to look at some of the details. So this is what is in the new Title 24 California Energy Codes, and a lot of people are switching to hydronics with chilled water, hot water, fan coils, air handlers, etc. But the main takeaway is one system can do 3 independent operations, 3 capacities, 1 power feed. That allows us to really simplify the mechanical infrastructure of the system, optimize energy sharing. So instead of having a COP or coefficient of performance of, let's say, 3 or 4, you can really optimize that to a COP of 7 or 8 and combine those loads together like you have done before. And then with some of the advanced defrost designs where we can have an always on active defrost with no performance derate, meaning we never have frost on the coils, or some other great grid flexibility things. It's really a fantastic project. Next. And then on the refrigeration side, you can see a lot going on here, but same exact heat pump, same exact applications. But instead of this time, we're running a liquid feed out to some cold evaporators in this space. We have freezers and coolers. We can now embrace the simultaneous heating and cooling and do things like hot fluid defrost that's milder, gentler, and a lot more dynamic and responsive. And we don't have to pay for electric resistance or reverse cycle hot gas defrost and all the energy associated. Make all your heating while you're cooling. Same thing, we can add in CO2 thermal storage that's on the bottom right, and we can now optimize for peak load shifting and take industrial cold for the first time really and bring it into a much more volume dense form factor. CO2 is about 9 times more energy dense than water, so everything gets smaller and it makes industrial level cooling storage possible. And then add in the fact that you can make hot out of the system, and it's really incredibly robust for an entire facility. And with that, I'm going to pause here and turn it over to my dear friend Roshan.
Thank you so much, Sean. It's amazing that this equipment is able to accomplish so much. And Roshan, would you like to come on camera now?
Yes. There you go.
Great, thank you.
Thanks, Sean. All right, I'm Rong-Xin Ng. I'm a research engineer at the Berkeley Lab. As a national lab, and we have been involved about laboratory and field demonstration of the proposed heat pump system in the large commercial buildings as well as in commercial cold storage. And I can talk about the energy and the demand performance point of view from the point of view of measurement and verification. And go to the next slide. So here's the demo site of our commercial cold storage, which is Straws facility. You can see this picture. We will test off our proposed system in 3 space, commercial cold storage space, 2 coolers and 1 freezer space. In total, it's about 2,600 square feet, but for the entire facility, it's over 70,000 square feet. And you can see this is a CNI facility, and it's located in PG&E's territory. As far as I know, it has a very high demand charge across both summer and winter time, especially on peak period. This is what we're going to use our proposed system to take care of this and demand performance. So regarding the storage type, so as I just mentioned, we have three type of space, but there are two major, which is freezer and cooler. For the freezer, I believe this is a space we can store the ice cream, and the temperature about -30 to -35. And for the cooler space, it's used to store the dairy milk, and the set point is roughly about 35 Fahrenheit degrees. And in total, in terms of low temperature refrigerant system at the freezer and medium temperature range, sorry, I suppose medium temperature. In total, it's about 550 mph for the cooling capacity. And I need to point out the most important element in this scope work, which is the electric defrost. As you can see, we have about 33 kilowatts of the electric resistance to functional as a defrost process in the refrigerant systems. And this is the problem we can tackle by using our proposed systems. Can you go to the next slide? So before we start to install this proposed system at the demo site, we construct an engine model and evaluate the existing system performance, especially for the electric defrost. You can see the right bar plot on the bottom, on the both side, left side which is summer peak day, and the right side which is wind peak day. So in the existing systems, we have scheduled defrost control process, which is for each time of defrost about like 20 to 30 minutes. Sometimes goes up to 40 minutes. But you can see we have 4 evaporators in those 3 storage space. And definitely, I mean, in the traditional control of the defrost process is always going to be, not stacking all those processes at the same time, just in case to avoid the peak demand, aggregate demand power from the defrost process. But even though this process of this defrost process can have impact on the total refrigerant system's power demand, it may not have that much impact on some peak day because the compressor will dominate the overall system demand load. But for the winter time, the start up and the trickle on of pressure over the defrost process, it has so much influence of the power demand, especially for the load pattern. So this is what we think about, okay, how we can propose or develop advanced defrost control process, as well as the new idea about using this liquid CO2 storage tank to take care of the peak demand. And let's jump on to the next slide. So here is the overall architecture about optimal control of our flow CO2 heat pumps installation at the commercial cold storage. And Sean already walked through the installed system at demo site using the defrost fluid storage in place of existing electric resistance. And we begin to install the cold liquid CO2 thermal storage tank to shift the peak demand of the refrigerant system load to off-peak hours, as well as an additional benefit from this heat pump, we can generate additional hot water in terms of heat recovery from the system. So Flow's heat pump has onboard controller, which has a standard communication protocol backlight, and we going to have a edge gateway to communicate to this controller and get data from the controller dispatch the control sequence back to the heat pump. And everything we have that model predictive controller as well as a communication agent that can communicate to the grid, receive the price signals as well as the demand response event signals from the grid side, and then to dispatch the optimal control sequence back to the heat pump, and to either reduce the bill, reduce the carbon emissions, just name it the objective of what we can do. And I need to point out, it's the controls, the optimal control sequence, all based on the real-time monitoring of the system, refrigerant systems. And can we jump down the next slide? This is a preliminary result from our model, and it helps us to understand how the control algorithms to be developed, and also how the algorithm performs before we put in the real system. On the left side, so I make a plot of the demand duration curve across the entire year, which is by 50 minutes interval. The blue line, which is the existing total power distribution across the entire year, and the orange line, which is we put in the hot water defrost or either other type of hot gas defrost or off-cycle defrost in place of existing electric resistance. And this is, we can see the new curve of the refrigerant system demand. So we can tell that in some peak day, we may not have that impact on the load reduction, but on the transition season as well as the winter season, we definitely can drop the overall system demand. And the control algorithm we can install at the air gateway going to trigger as well as the evaporator performance begin to degrade and synchronize the power surge from the full evaporators. So this is all based on the real-time monitoring performance as well as from our model predict controller. On the right side, which is the performance of installation of a liquid CO2 storage tank, and upper plot, which shows the discharge on the peak times from 4 to 9 p.m. And this peak period is same peak period across the entire year. And the only difference about the mid peak period, but here we just propose to charge for 8 hours during off hours and discharge the cold CO2 refrigerant to switch off the existing compressor and reduce the system demand. And you can see how the charging discharging works on the peak day. And let's see the next slide for the performance. So here we go. So as you can see, the proposed system definitely can reduce the monthly, both energy and demand costs significantly, and the majority of savings come from the demand charge savings, especially for the on-peak period. For this large C&I facility, 1 kilowatt of the demand charge, which is about over $35, and it's only for the on-peak demand charge. And you think about on-peak demand charge, mid-peak demand charge, as well as max demand monthly charge. That's how we can see the majority savings from the these proposed systems. And annually, we can receive like $9 per square feet, which is for this site, which is like $20,000 in total for a year. And most important, which is carbon emission savings. Since we utilize the CO2 storage tank to shift the on-peak electricity we can call it a dirty electricity consumption to more green electricity during off hours. We can receive like 15 metric tons CO2 emissions. And overall, we have like roughly about 28 to 44% of the cost savings by install this system in place of the existing one. And we're going to test out, and we can test out in the coming year, and we'll see how it comes at the end. Thank you.
Thank you so much, Rangjin. It's great to see both the carbon emissions decline as well as the cost decline. It's great that both those things can be accomplished. And with that, we're going to have a little panel discussion. I'm going to stop sharing my screen so that we can see each other a little bit better. I again welcome any questions in the Q&A. I noticed that there was a question that came across in the chat as well as the Q&A. I'd like to start with the first question in the chat. And Rangjin, maybe this is a good question for you. The question was, with the answer system, can it integrate with air changes, fresh air requirements for optimal energy savings while still keeping the building healthy?
The answer is yes. Definitely Sean has a better position to answer this question, but Flow does has an onboard controller, which has standard communication protocol, the backnight communication protocol, which is very straightforward to integrate with the existing BA systems. That's right, Sean?
Yeah, that's right. I would just add a little bit. We can make cooling, and then we can make chilled water and hot water at the same time. We can't control the fresh air. We need an air handler solution for that to bring in and manage the fresh air into the space. So let's say in a supermarket application, you have your cold chain, and then you have your DOS, you can bring in conditioned air to trim out the space. We can provide the chilled water, hot water to make the cooling or dehumidification work there with the same system that makes the cooling for the process. And then the communications protocol, all standard BMS points are out there, BAS points, Modbus, BACnet, you name it. I don't like LAN just because it's kind of a pain sometimes. But other than that, and also we do have an onboard web server that is available standard in products that has a web app, web portal that you can get into, as well as onboard controls. It all stores locally and through an industrialized process secure gateway, so you can see real-time monitoring and real-time commissioning. So now you can really dial it in so you don't have problems. And just rely on a data sheet and never go back and test. We firmly believe in validating every step of the way and making that available to everybody.
I think we greatly appreciate that too, Sean. It's going to be such a great resource for everyone who does work in refrigeration and HVAC. I wonder, Doug, if you might be able to help with another question. I was wondering about the ability of the workforce to help support these new systems. It relates to the question in the Q&A, which relates to ongoing maintenance like coil cleaning for HVAC and refrigeration systems. Are you seeing that there is development in the workforce so that they're experienced with this type of system?
Yeah, let me start with this. When we talk about quote unquote, decarbonizing a system, the work that goes into trading out a current system with, let's say, a heat pump of this kind is really in some ways one of the more straightforward aspects of the whole problem. It's the fact that everything else also changes. So your power management is going to change, your maintenance will change, your operating schedules may change, your peripherals may change. It's just like buying electric vehicles instead of gas vehicles. There's just an entire systemic ripple that has to go through. So when you talk about workforce, that workforce can be very diverse. I can tell you that in the kind of contractor and engineer space, groups like DMG are working diligently to train people on how you operate, maintain, or design heat pump systems. But also in the facility management space, organizations like the International Facility Management Association, or IFMA, are really dedicated to the position of a facility manager and its capabilities, and they're doing training. Local workforce organizations are equally trying to train the next level of technicians and others in this space, in the decarbonized workforce. So there's a whole host of people that are working together. And I think what's important is it's not just who needs to flip the switch or set the dial. There's a mindset that needs to change across the entire organization when you do that. That's why leaders like Strauss are really important, because they're up for that.
Thank you for that. And then another question, Sean, I wonder if you might be able to talk to us a little bit more about how this affects the quality of the product. In this case, we're talking about ice cream. Could you talk to us a little bit about that?
Yeah, so every industrial process has their secret sauce, right? We can't disclose how the yumminess is made, but a lot of this relies on things like rapid temperature changes affects things like crystallization of products, or how fast you freeze something affects the moisture content as it solidifies. All these things really matter when we're talking about industrial process and applications like that. So with a system here that has a milder and gentler defrost, initially when we looked at this project, we were having 75 to 90 degree hot water coming out of the condensate pans on the evaporators. That means the space is getting really hot. If we can make that a gentle, maybe keep that in the 40-degree range, you're not going to have as much of a temperature oscillation and swing, so that now you can really dial in your process a lot tighter than you have. Same thing goes with precision control and balancing all that out on a system. And we use electronic valves and VFDs for everything we do. And then having adaptive energy models to load shift, so the grid doesn't say, hey, I got a brownout thing, you should load shift, and then click the switch. Well, if you got a load shift, facility operators, and especially on the industrial side, have a chance to say no oftentimes. But with this CO2 storage option, they have an opportunity to say yes and truly participate without any detriment to their core business.
This all sounds so great. There was another question in the chat that wondered, are there any trade-offs? What is stopping everyone from using this system? And Doug, would you?
Sean?
Or Sean, yeah.
Oh, there's all kinds of things.
So many answers to this one.
The simple answer is the transcritical part of the engineering equation wasn't solved well. There have been people marching along. CO2 is the first refrigerant that was used, and it's been around for over 100 years in different iterations. And the current iteration's been around for about 30 years. But copper, on the other hand, can only go to about 700 psi if we're lucky. Now, that means if I want to do a thin wall copper system that is the lowest possible cost point, I can't use a higher pressure refrigerant like CO2. We just solved it by volumetrically, CO2 is about 4 times more dense. So we use a smaller bore stainless steel tubing, off the shelf type products, and that solves all of it. You just have to adjust your manufacturing process accordingly. There's billion-dollar plants built today around not doing that. So they would have to rebuild from the ground up on a lot of organizations, and that's frankly hard. So that's where Flow really came in as a company, and with a lot of great partners that make a dent in that.
You know, I'd add a couple of things. You know, I mean, the market for current refrigerants is accompanied by equipment that is comparatively inexpensive. I hate to use that word, but let's say it's comparatively less costly. But at the end of the day, that paired solution doesn't address the actual GWP problem that we're trying to address. In terms of, let's say, everybody doing it, the system that was installed 4 years ago that still has 20 years of life may not be the highest priority and shouldn't be the highest priority if you're looking at making, effective financial decisions. But all that being said, comparing the cost of a system like, let's say, a flow system, we're all looking forward to a competitive economy. So, other CO2 heat pump systems, it's not a simple fact of first cost versus first cost. It is net present value of the first cost, the cost savings, the overall maintenance savings, and other factors in comparison. So that 20-year lifespan may start to become financially smart to consider a change even 5 years down the road, not 15. It has to be looked at carefully, and it's something that we want to make sure is clear, and as we looked at this work as well. So part of it is the market and the market drivers, and the people that own that market want to make sure that it's hard to make a principled decision. But we also think that the financial trade-offs and the analysis behind that has to go a lot deeper than price tag.
Yeah, or at least first price tag, I would add. Once we kind of get into the weeds of how to get the real cost of a system, we often see it's a 2 to 5 year payoff to just simply make a transition to something like this. And that goes anybody outside of flow as well.
Wow. That's pretty quick return on investment. What is the lead time for a system like this one?
We're about 36 weeks or so right now for equipment once we have a project designed in. So a little over half a year.
So good to include in that consideration of time.
And we are building out additional things. So there are some quick ships for smaller projects available, but for large projects, we need to design things right. It takes a little bit of time to get a building transition.
Sean, comparatively, that's not very long compared to lead times for any conventional equipment.
And well, a lot of chillers and racks are over a year right now.
Yeah.
It's a time of transition, for sure.
Yeah.
And Rangjin, I wonder, with the grid interactive aspect of this project, which is so exciting and so important to, possibly all utilities around the country, is that work happening? Like, is the local utility starting to make adjustments in the way that would be helpful to them?
Yeah. So actually, demand response has been in the market for over 20 years. And especially for the commercial cold storage and refrigerant warehouse, there has been participating in the grid market in reducing their peak demand as a load, to provide load flexibilities. But differently is like, each type of refrigerant warehouse and cold storage, their process load are different. And in our previous demo site, we can adjust thermostat set point by a few degrees. Let's say you store the meat and other like wines, all these. They have some range to adjust to reduce the refrigerant system load. But for this one, ice cream, and we don't want to mess up their operations. That's why we introduced the concept of the storage tank.
Yeah.
And especially for the grid interactive point of view, which is like, we have that, we put everything in that edge gateway, controller, communication agent. So to interact with the grid, receive signal, trigger the optimal control sequence, dispatch to the heat pump unit, and then we have the real-time adjustment of the sequence, make sure we deliver to the grid as we propose to do. But most important, we want to, there's no impact on no interface with the existing system operations, especially for space temperature control.
I'll just mention there's a number of on-market solutions for delaying the need to turn on the chiller, so to speak, phase change materials and other kind of thermal storage activity. We're doing a novel thermal storage pilot as part of this work. So those things have been around for quite some time. As Ranchan said, demand response has been around for quite some time. I think the challenge here is the economics of any of those solutions can be a little challenging, and as Ranchan mentioned, could be operationally an issue. It needs to be something that works in the physical space and doesn't mess with product. You do not mess with peak ice cream. I have been very well schooled in this, so it needs to be something that fits the operation specifically.
And also that you point out at another point, which is like you can see over the last 10 to 20 years, the on-peak period has been adjusting over the time. You know, from like 12 to 6 o'clock to 2 to 4 o'clock, now 4 to 9 o'clock, because of the additional, you know, penetration of the renewables on the grid. And so which is like we need to make the system more adaptive to the grid.
Yes.
Yeah. And one more thing with thermal storage, while it's wonderful and great, chances are nobody has space for anything when they're thinking about retrofits. So you want to make it as tight and compact as possible. So let's say I'm doing ice storage. It's a huge volume because ice expands when it freezes compared to water. So like a CO2 or a phase change material might have a phase change might be a 4 times reduction on the volume of required for the thermal storage, and CO2, as we're demonstrating here, is going to probably be about a 9 times reduction in volume, which is from here to here. So it makes a big difference.
Yep.
Yeah. Very interesting. We have just a few minutes. I just wanted to offer each of you an opportunity to leave our guests with any final words of wisdom.
I'll just start with some gratitude to my partners and certainly to NBI for this opportunity to talk about the project. We've shared a link to Pathways. We want you to stay involved, and we want you, please, to stay with us as we go through this and many other projects. And we want your feedback so that we can continue to serve the industry with important insights here.
I'll jump in as well. Exactly what Doug said. And then also, if you want to get involved in any projects, whether you're in the technical, wanted to join in on participating in these projects or doing something else and work on your own projects, we have a lot of resources all over the country doing different things. So please reach out to all of us and jump in. And thank you, Susan and NBI, for putting this on.
Yeah, thanks so much, Susan and NBI, for putting together this webinar. And if you're living in Bay Area, you know, we can have our laboratory testing of the heat pump in the early next year in January. And also the demo site at Strauss will be next year. You know, we're going to keep you posted of any progress of the laboratory testing and field demonstrations.
Well, that's great. I also want to express my deep gratitude for each of you for joining us, and I'll be keeping a close eye on this work as it moves forward. Thank you and have a good day.
Thank you.
Thank you all.
Thank you, everyone.
All right, bye.
Bye.